Welcome back, Shayla area. It's time to kick off Unit 2, Chemistry for Honors 8th Grade Science. Things are going to start getting interesting. So it wouldn't be chemistry without a periodic table. We are going to learn a lot about the periodic table. This is actually going to be the primary tool that you're going to learn how to use. You're going to learn what all the different columns are for, what the rows are for, what all the different numbers mean and the symbols. And you're even going to pick one of these and decide which one of these you are the most alike. We're also going to learn about what atoms look like. We're going to learn who these people are and what they did and why they're important. And we're going to learn about how atoms bond together. We're going to learn about bigger molecules like these things. This is a soap molecule. We're going to learn about how to start chemical reactions. We're going to learn about a lot of stuff in the chemistry unit. So let's get started. So part 1, chemistry unit split into 3 parts this time. And part 1 is going to be about how matter is shaped by heat and pressure. So remember, matter is anything that has mass and takes up space. So any material that has mass and volume. And we are going to talk about what happens to it when we add heat or take away heat, and when we add pressure or take away pressure. So to begin, we need to start talking about heat. So just what is heat? Well, to talk about heat, we need to talk about temperature. Temperature is the average kinetic energy. So remember, kinetic energy is the energy of motion. So temperature is actually things moving. It's the average kinetic energy of all the individual particles in a piece of matter. In other words, temperature is literally how fast the atoms and molecules are vibrating. So in any given material, let's pretend this screen was actually something that we could measure the temperature of. You can imagine there being lots and lots of molecules and atoms. And they're all moving at different speeds. So maybe this one's vibrating like this much, and this one's vibrating a lot, real fast, and this one's vibrating a little bit, and this one's vibrating this much, and this much. So they're all vibrating at actually different speeds. We would take those speeds and add them all up, divide by how many molecules there are, we'd figure out the average, and that is actually your temperature. So all the particles are always moving at different speeds. Temperature is the average of all of them. The unit that we use for temperature is called degrees. Degrees. And the tool that we use to measure temperature is the thermometer, as I'm sure that you've used a lot of. So who are the people that we need to know about for this lovely temperature scale and thermometer? Well, the first person you need to know about is Daniel Gabriel Fahrenheit. I'm sure you recognize the name because this is the temperature scale that we use in the United States. Note, this is not the SI temperature scale. The SI temperature scale is actually called Kelvin, and it's based on Celsius. But we in the United States use Fahrenheit. We'll talk about Kelvin and Celsius in a few moments. So Daniel Gabriel Fahrenheit was a pretty important guy. He invented the first modern thermometer. So when you look at the thermometers that we use, yeah, that was pretty much his idea. So can't imagine that anything that I will ever make will still be being used, 400 years later. That's pretty neat. Anyway, the way a thermometer works is you have a sealed glass tube and you have a liquid in there. And as we talked about prior, when you heat things up and cool things down, they can get bigger and get smaller. They can change in actual size because of these molecules and the atoms. So if you think about it, if a liquid is nothing more than a bunch of molecules vibrating and moving around, and we add heat, we add more thermal energy to that system, those atoms and molecules are going to start to move around faster. The average speed will go up. And if you think about a whole group of people, if we had a whole group of people that were crammed into one space, and then we told them all to start moving faster, and then we told them all to start moving faster and moving faster, the size of the group, the amount of space that it would take to hold that group would get bigger, would need to fill. And that's what happens with the thermometer. As the liquid heats up and the molecules in the liquid start to move faster, the liquid requires more space and it climbs up the tube. And when you slow the molecules down, it allows them to come closer together, and that causes the liquid to shrink, and then it goes down the tube. So that's how essentially a thermometer works. So what Fahrenheit did was he put different liquids in these glass tubes and sealed them, and then changed the temperature, like put it in boiling water, put it in freezing water or whatever, and would put marks on the glass for where these things happened, and then figured out which kind of liquids would work best. We used to use mercury in our thermometers, but mercury is really not good for you. So we stopped using them in public places, like in schools and stuff like that, because when you break them, it's like a big deal to clean up all the mercury. So now the red liquid that you see in thermometers is actually just alcohol. It's like rubbing alcohol, and it has like red dye in it, just so you can see it a little bit better. But anyway, the two important temperatures in the Fahrenheit scale, you do need to know these. These are the ones we use in the U.S., so you really should know them anyway. Water freezes at 32 degrees Fahrenheit, and it boils at 212. Just another great example of how the American system of measurement uses nice round numbers. So anyway, we have Fahrenheit. That's what he's important for. Those are the freezing point and boiling point in the Fahrenheit scale. Next up is Anders. Love that name. So Anders Celsius was a child prodigy. Celsius was the kind of person that in their teenage years was like actually discovering things and being like a huge important person in society. He did a lot of things in science. He gets a lot of credit for a lot of things, but the one that we remember him for, because it bears his name, is the Celsius scale, or the centigrade scale of temperature. And what's really interesting about it is that he never used this scale. So what we call the Celsius scale is not anything that Anders Celsius ever actually used while he was alive. So his scale that he made had the boiling point of water at 0. 0 degrees is what he called the boiling point, and he called the freezing point 100 degrees. And I didn't say that wrong. He used the smaller number for boiling point and the higher number for freezing point. So it would seem, from what we're used to today, that the scale was upside down. And there's interesting discussion about why he would have done this, and how an upside down scale would be beneficial sometimes. It's an interesting talk that sometimes people have. But anyway, he died, and then Carl Linnaeus, who is a name that you should remember from your 7th grade year, Carl Linnaeus, or Carolus Linnaeus, we just call him Carl Linnaeus. He is the guy who created the system of taxonomy that starts with kingdom and ends with species. It's actually not the most current one. The most current one was made by Carl Woese, and it starts with domain and then goes to kingdom, but I'm sure you learned the kingdom, phylum, class, order, family, genus, species list in 7th grade. He is the guy who came up with that system. He also is the person that took Celsius's scale and said, you know what, this doesn't make any sense. I can imagine him like if there were Post-it notes back then, like just moving the Post-it notes and flipping them around. And he made freezing 0 and boiling 100, and did that pretty soon after Celsius died. And that's the scale that we use today for Celsius. Here are the next two are probably ones that you're not going to know. So these are ones that you're going to have to learn. But one of them, and the most important of all of the temperature scales really, is the Kelvin scale. This is the SI system of measurement for temperature. This is the temperature system that scientists use. If you travel to other countries and ask for a temperature, they're going to tell you in Celsius. But if you're talking or reading or doing anything about science, all temperatures will pretty much be in Kelvin. Now, the Kelvin scale is named after this guy named William Thomson, who went by the title Lord Kelvin. So that's why it's called the Kelvin scale, because that was what he went by. He did some really important things in science and really important things for England, and the Queen gave him a knighthood and he then became Lord Kelvin. They made that area up just for him. It's actually named after a river near where he was born. The stuff that he did was he was pretty much the guy who made it possible to string a cable from like across the Atlantic Ocean to like connect the United States with England so that they could send messages via cable instead of having to write them in a letter and send them by ship. Kind of really started globalization and whatnot. He's the guy who did that. He did lots of things. It was pretty important. He was actually one of the most outspoken people against Darwin when Darwin's theory of evolution was starting to come out. He was definitely an opponent of Darwin. But anyway, what William Thomson did and what he's most well known for because of this temperature scale is he figured out something called absolute zero. Absolute zero is pretty cool. If you think about temperature being a speed, so temperature is how fast the atoms and molecules are moving. Well, imagine then if you're cooling it down and cooling it down and cooling it down, and those things, those molecules and atoms are vibrating and moving slower and slower and slower and slower. Well, if you follow that line of thought, then eventually you would get to a point where the molecules are no longer moving, where they are actually sitting still. They're not vibrating. That also means that if you go down all the way into the atomic level, the electrons are no longer going around in circles around the nucleus. Everything is at rest. There is no motion. And this is called absolute zero. And this is the starting point of the scientific temperature scale. This is zero. So since you can't get anything lower than absolute zero because you can't move the materials any slower than stop. So there's no such thing as a negative temperature in the Kelvin scale. So he used the same size degrees that Anders Celsius used for his system. So the temperature of the Kelvin scale and the Celsius scale are very, very similar. It's the same exact temperature, it's just a few hundred degrees off. But the size of it is the same. So it's not like how 1 degree Celsius and 1 degree Fahrenheit actually represent different amounts of heat. So 1 degree Kelvin and 1 degree Celsius represent exactly the same amount of heat. So it's abbreviated degree K, and it is the SI unit of temperature. So how is it that he figured out this absolute zero thing? Because it's still a theoretical temperature. We've never actually achieved it. In fact, in trying to achieve absolute zero, we don't think that absolute zero exists anywhere in nature. And what's interesting is if you think about the entire universe, it's a pretty big place. We believe that the coldest places in the entire universe have been created on our planet. That through our search, our quest to try to reach absolute zero in some kind of like environment, that we have created temperatures that are even colder than the emptiness of blackness of space, which is also pretty neat. So what Kelvin did and what people can do to figure this out is if you have like pure gases, for example, so here we have a gas A, which could be like oxygen gas, we'll say, and gas B, which we could say could be like chlorine or nitrogen gas or something, and gas C, which maybe that's like carbon dioxide. So these are pure gases, and we somehow are able to measure the speed of the molecules. And as we cool it down and we continue to measure the speed of the molecules at particular pressures, then we can plot a graph. And the graph ends up making a line. And what's interesting is while the speed of the molecules is different for every kind of material, that's because of the actual sizes and masses of the molecules, the point at which all of these lines reach the speed of zero is the same for every substance. And so if you look, the line is solid because these are where we've been able to gather data, and then we reach this point and we just can't make this gas any colder. Nothing we do scientifically, we can't slow those molecules or atoms down any more than that. So that's where experimentally it stops. But you can see that it makes a line. And you can extrapolate that line out to this spot where speed is 0. And we can do the same thing for this gas and this gas. And every time you do that, it reaches exactly the same spot, exactly the same number of degrees for 0 speed. And that temperature is negative 273.15 degrees Celsius, or as we say, 0 degrees Kelvin. This is absolute 0. You cannot get any colder than this. This is, when they say it's like negative 10 degrees outside, well, you could not say negative 275 degrees outside, because that would be colder than it would be possible. As far as we know, there's no upper limit to how hot things can get. Well, I guess they would eventually probably reach a point where they would completely disintegrate down into like individual little specks of what atoms themselves are even made of. But so I don't know what the upper limit would be, but this is definitely the lower limit. And since suns and stars can be billions of degrees, that upper limit must be pretty high. So absolute 0, negative 273.15 degrees Celsius. It would be in your best interest to remember this number. Definitely you're going to need to remember that number to answer 1 or 2 trivial questions on quizzes or in exams that you see from here on out. So if we were to translate the boiling and freezing points of Celsius, which are 0 and 100, which I don't think that was in the PowerPoint a minute ago. I wonder if that slide didn't play. If that's the case, on the previous slide, remember that in the Celsius scale, water freezes. Where's my eraser? Back. There we go. Back. Freezes at 0 degrees Celsius and boils at 100. Oh, yeah, it wasn't there because we talked about how it was flipped around backwards. All right, so anyway, in the Kelvin scale, water freezes at 273.15 degrees Celsius, and it boils at 373.15 degrees Celsius. That's because when you start at 0 and you go 273.15 degrees Celsius up the scale, you end up at 0 degrees Celsius. And then if you go another 100, you end up at 373.15 degrees Kelvin. So the size of the degree is the same. There is a 4th scale called the Rankine scale, and it's named after William Rankine. William Rankine was a pretty important guy when it came to designing combustion motors, like kind of the type of engines that we have in our cars, where you have to like burn a fuel to run a piston, which then turns cranks, which then turns wheels. Those kinds of motors and engines, William Rankine pretty much designed. Much of what he did is still used as like the basis of how all of those motors are gone. Like some of the laws about how you build a motor have his name on them. So he also had a temperature scale that he started at absolute 0 because he was figuring out absolute 0 at the same time that Kelvin was. So he also claims to have discovered it. But he was more American than he was European, so he used Fahrenheit in all of his experiments. So his scale uses the same size degree as a Fahrenheit, but starts at actual absolute 0. And since nobody else uses the Fahrenheit scale, this system of measurement for temperature just simply doesn't exist anymore. There's not a single person on the planet who would measure anything in degrees Rankine. But for historical purposes, I thought you should know about them. So a couple thermometers, easy questions. The temperature of this thermometer is, I feel like Dora the Explorer, I'm like waiting for everybody to shout out to the screen. And the temperature of this thermometer would be, yeah, of course, 30 degrees Celsius and negative 5 degrees Celsius. Any thermometers that I show you in class are always going to be degrees Celsius. I don't have any thermometers that measure anything in Kelvin. This little chart here is something that you're going to want to put a big star next to because you are going to need to know these temperatures. So much like you need to know things like how big a kilometer is in comparison to a mile, or how big a kilogram is in comparison to a pound, this one's more important than those, because if you travel anywhere, the thing that you're going to need to be the most aware of on a day-to-day basis is how hot or cold it's going to be outside. Because if you travel anywhere, you're going to be packing different clothes. And if you look at the news the night before, you can't understand what they're saying because they might be speaking a different language. But it scrolls across the bottom of the screen that tomorrow's temperature is going to be 30 degrees. And you're like, wow, I went to a beach somewhere in like the east coast of Italy and I brought my swimming trunks and it says it's going to be 30 degrees. I did not pack appropriately. But remember, it's a different temperature scale. So there are 4 temperatures, and if you know these 4 temperatures in Celsius, you will be able to function and have a working knowledge of any temperature that you see in Celsius. So the 4 temperatures that you need to know are boiling point, and as we already said, that is 100 degrees Celsius and 212 degrees Fahrenheit. You know those, we can blow right past them. We have freezing point. Freezing point is when it would be nice and cold outside, like snowing. That's 32 degrees Fahrenheit, or 0 degrees Celsius. The next 2 are body temperature. So let's say you are a European student and you don't want to go to school, and you wake up and you tell your mom that you had a fever, and she takes the Celsius thermometer and she checks your temperature. If you have a fever, how would you know with a Celsius thermometer? If it didn't have Fahrenheit on it and you were in a different country and you were trying to check your temperature, you wouldn't know what to look for. You wouldn't know if you had a fever or not, beyond just feeling how warm you were. So what body temperature is in Celsius, can you try to figure it out from these numbers over here? Which of these do you think is body temperature in Celsius? Well, which one's body temperature in Fahrenheit? That's this one. So which of these 3 do you think is going to be equal to 98.6 degrees Fahrenheit? Did you pick this one? So 37 degrees Celsius is human body temperature. So if you have a human, if your thermometer reads 37, then you are perfectly fine. If it reads 40, you have a very significant fever. That would be like a pretty bad fever. And then the last 2 are room temperature. So this is kind of like what you would think, what would a person set their thermostat for their furnace. Typically, like furnaces come preset with their thermostats at 70. Some people prefer at 70. Some people prefer things more in the 60s. Some people prefer more things in like the mid 70s. But a nice average temperature might be 70, and that equals out to 20 degrees Celsius. So these are the 4 Celsius temperatures that you need to know. So 0 is freezing, 20 is room temperature, body temperature is 37, and boiling is 100. So if I ask you questions like, nice football weather outside, it's fall, you're going to go to the Steeler game, what temperature in the Celsius scale would be like a chilly night at a Steelers game? And you'll have to be able to pick a number. And I'm not going to say 20 or 37 on the test. I'm going to say things like 5 and 23. So you kind of have to have a sense of where these benchmarks are. So would a chilly Steeler game be colder than your house? Yeah, that's why you have to wear coats and stuff. So the right answer to this question would be something less than 20. So you wouldn't pick 23 or 40, for example. You know how you can tell this is an old chart? I just noticed this today while I was looking at it to get ready to do this, because the girl is talking on a phone that's attached with a cord. I saw that and I was like, that's pretty funny. I bet you that none of the students watching this video have ever talked on a phone that was attached to a cord. And that takes us to the first booby trap. You might want to put a little mark in your notes so that you know that that's what you're supposed to study up to. For booby trap number 1, 16 questions. Thanks for hanging out with me, and I will see you in class soon.